the last minute notice, I'd like to thank Microsoft for sponsoring the venue and coming on the last minute notice, because I only announced Sunday night. And last but not least, welcome. Thanks for Traveloka to come to speak today. We have Deb, who is a data science lead in Traveloka, focusing on NDS, which is natural language, computer vision, and speech. And then we have Yixuan, who is working on recommender system. So without further ado, please give a round of applause for them.
Hey, hi. Can you hear me at the back? Or all right, cool. Okay, so we don't need the mic. That's great. I usually start this off by asking people if they've heard of Traveloka before. That's probably a moot question, given that this has been plastered on the wall for about half an hour now. But in general, how many in the audience have?
Sorry, can you please use the mic?
Yeah. Okay. Fine. Well, thank you. To use the mic, we must find the mic. Okay. Here we go. Is that? Okay, can you hear me? Yeah? Yeah. All right, okay, cool. So, I'll repeat the question. How many of you have heard of Traveloka as a company before? Oh, wow, okay. Yeah, okay, so people from Traveloka, please put your hands down. Okay, so who, I thought in that case, I mean, it's always useful to do a bit of an overview about who we are, because we don't really advertise as much in this part of Southeast Asia. Interestingly enough, we're actually a leading online travel company in the region. You may have heard of us, but you may not know to what extent we do operate in the region. We're actually, I mean, most of you probably associate, those of you who have heard of us, probably associate us with flights and hotels, but we actually do a lot more. Actually, this is probably a not comprehensive portfolio. In fact, our fintech colleagues at the back will probably say, hey, where are we? But this is kind of what we do. We have about 100 plus airline partners, quite a few hotels in over 100 countries. From a data perspective, what might interest you, and certainly does to us, is we have about 1 million daily users and at least 40 million apps that 40 million times that people have downloaded our app in the region. This is where we operate. In terms of offices, so the only exception to office versus operations is India. So we only have a research presence in India, so we don't actually offer our platform or app as a service. So Singapore, Malaysia, Vietnam, Philippines, Thailand, Indonesia, and recently Australia. Okay, so that's corporate HR did ask me to just make sure you say good things about Traveloka. So we love working there, and that's certainly job done on that front. So let's talk a little bit about machine learning at Traveloka. So before we get there, I thought I'd just introduce how we're structured. So naturally, you can think of us as comprised of central business units. So our products are owned by business units. So for example, flights and hotels, these are products. They're owned by BU. We have central engineering teams who back these up. We've got corporate functions, so HR, etc. And then we have the data team. And the data team, what we want to do is enable the company to make better decisions faster, generate actionable insight, create and nurture a culture of data-driven decision-making, and essentially create long-term capabilities and expertise to drive value for the business. Now, I hope for some of you who are noticing that we don't have goals like building the data lake or making an AI team. It's probably not a good vision and mission to have. I think doing it for the sake of doing it is probably a foolhardy endeavor. So we're focused on basically enabling business impact. And what we do own to get there is things like the data lake, our core data platform, which makes sure that any machine learning models that we do deploy to production have the features they need in real time. We've got our analytics teams, and we have AI and ML. I think I try not to use the word AI as much as I can. I think we have a running joke that if you're writing code, it's machine learning. If you're doing a PowerPoint, it's AI. So I guess okay. And of course, we have A/B testing, which is quite a critical component in pretty much any machine learning endeavor. In fact, every company does and should have A/B testing. Okay, so within the data team, we spoke about machine learning. At Traveloka, we try and segment them into two very big, broad buckets. We think of them as machine learning for humans and machine learning for machines. So ML for humans is where we kind of generate our insights. We have a lot of models. So for example, complex metrics, we use statistical measures to come up with those and make sure that they're valuable to the business. But this is also where we house our experiments unit, as well as our data marts. Machine learning for machines is where we think of them as data or machine learning products. Right? So you've got insights and you've got models, but there are also certain components of the platform which we want to automate or augment. And that's where we leverage machine learning to really get them to the next level. We also do R&D. I should say that when it comes to R&D at Traveloka, we're very explicit. We're not a blue sky research organization. I think we're not at a stage where we feel that that's truly valuable for us. But we're certainly keen to innovate, and so we certainly do a lot of R&D in alignment with what the business needs us to do. Okay, so that's us, some of us. I do apologize to the women in the room. I'm so sorry for such a monochromatic, non-diverse picture. Yeah, we definitely have some wonderful female data scientists and analysts at Traveloka. This is just some of us, so you may see Yushuan here as well, who's kind of with us. So this is a couple of our teams. So the NBS team, which is NLP Vision and Speech, and our recommendation systems team, just before we're off doing some AI, right? Okay, so the theme of the talk is NLP at Traveloka and how we have to work with a non-English environment. So what do we use NLP at Traveloka for? Where do we use it? So you've got the traditional, you've got chatbots. That's supposed to represent a chatbot, by the way, so yeah, it's a bit ambiguous. So essentially, yes, we've got sort of chat technologies, and they're yeah, Yushuan's going to man that right now, sorry. But we have review moderation. So if you think of the platform and how people engage with us, we've got a pretty active community. And they're very vocal about their feedback and how they want to express their disapproval or approval of the places they stay at on our platform. Now, at the same time, we need to make it a sane and safe place for everyone to engage with. So review moderation comes into play, and in terms of the loads that we get, if we needed to do it completely manually, it would cost us a lot of money to maintain that same level and quality of customer service. So this is where we do leverage machine learning and AI to help ease that. Customer support. So one of the core values that Traveloka really tries to espouse is top-notch customer service. So when people engage with our platform, we try and make sure we're delivering the best experience we can to them. And that's why customer support is very important to us. At the same time, we need to make sure it's scalable to do. So we do use that. Search, so if any of you ever, I probably don't need to go into too much detail into what search is. I think we're pretty much replaced with search with Google these days. Can I say that? Knowledge engineering. So here, basically, we're trying to understand the relationship between entities or things. And there's certainly a component of understanding how language plays a part in there, right? Now, okay, so that's how we use NLP at Traveloka. The other thing that kind of goes unsaid is Indonesia is our biggest market, and Bahasa is a language that is spoken throughout this region. It's very popular. So what's the challenge, right? What's going on? I mean, why is NLP in a non-English environment a factor? So it's interesting because this leads back a little bit to how sort of machine learning has evolved and transformed over the last 20, 30 years. And most of you, not all, but most of you probably encountered machine learning, after this whole deep learning hype cycle. Interestingly enough, the technology that powers deep learning at its core is quite, I wouldn't say ancient, but it's certainly been around for 30, 30 years. What actually happened is computing power and data caught up. That really caused an explosion. Some practitioners were able to make significant gains and leverage the hardware and data at our disposal to make that huge jump. And that's kind of caused this huge hype cycle. What's gone under the radar is a lot of the ancillary domains. So initially, it was all in the vision space. But domains like natural language processing actually relied on a lot of, I wouldn't say artistic endeavor, but certainly a lot of scientific research to power the core fundamental components. So you're talking about things like parts of speech tagging, So dependency parsing, where you're saying, well, this is a sentence, and how do you understand what these parts of speech that comprise the sentence, what's a noun, what's a verb, things like that. You're looking at named entity recognition, where you're saying, okay, so how do you understand that from this particular sentence, this means a person, this is a place, an organization, and so on and so forth. Word embeddings. So word embeddings are obviously, I think, from my personal perspective, one of the most interesting things that have come out of this deep learning revolution. They're probably going to be around for much longer than RNNs or LSTMs, hopefully. But of course, when it comes to non-English word embeddings, they're not as useful or as vigorously trained, at least in our experience. And that's probably a function of the fact that labeled datasets or datasets for research in NLP non-English languages are not as available. It's certainly for Southeast Asian languages. I mean, apart from huge exceptions like China, Mandarin, Cantonese, and certainly some of the European languages. But in general, for Bahasa, we don't find as much data. So we're missing the key ingredient here, right? I mean, if you think back to what's really powered this hype cycle, and this AI cycle, if you will, machine learning, live, and it's data, and we're kind of missing that ingredient. So the other thing, of course, as a function of that is baseline data sets. So you do some work, you do some research, you come up with some numbers, and you're like, I don't actually know if how good we are, because there is no agreed upon set baseline which says, okay, if you get a 40% complexity for your specific data set, for your language model, you're doing well or not, right? So that's difficult to understand. So you've done some work, but you don't always know how good it is until you're actually testing it out in real life. And this is kind of where Traveloka has a bit of an edge, because we do have a lot of data. So I kind of like to think of sort of the deep learning era and the components that you really need to get high quality NLP in 3 buckets. Again, this is meant to be a bit of a it's generous, so it's not highly accurate, but essentially, if you get your pre-processing right for your specific language, if you've got a good set of word vector embeddings, and if you are comfortable implementing and tuning your chosen deep learning architectural framework, I think you're in good hands. That's a good starting point for you to think about getting productive results in your chosen language. Is this going to stream? So, is that better? Is that better? No. Yeah. Okay. So, right, let's move on then. How many of you know what language models are? Okay, so all of you, fantastic. So I'll skip this now. Okay, so language models basically are a really simple to understand concept. What they're saying is, if you're given a specific sequence of words, if it's an n-gram, basically you're saying, given a sequence of words, try and predict the most likely next word. Right, so my name is, and depending on the corpus that you're playing on, it might be John, if it's a very English corpus, right? So that's what a language model is. ULM fit is a pretty nifty piece of research done by Jeremy Howard and Ashir Ruder, and they're kind of trying to say, well, a language model has these core components. We found a framework where you can train and tune your language model in 3 ways. So what they say is you train your core vector embedding on a pretty general corpus. Right? You're saying just train it on your Wikipedias and your news article data sets. Then what you should do is basically fine-tune it on your chosen task language corpus. So if you're customizing your specific language model to cater to customer support in the travel industry, this is probably a good time to introduce that corpus of data. And then you finally try and do a last stage, which is basically fine-tune the classification component. Now, okay, let me just move on. Because I didn't want to make, I wasn't sure what the audience composition was going to be, so I didn't want to make it too technical. And at the same time, I do feel that these talks sometimes, if you're really interested, there are some phenomenal resources which help you understand these things. What I was hoping to talk about is a lot more about challenges which you may not have access to in wider literature. So if some of these terms are a bit confusing, or if you're not as aware of these, I would heartily recommend reading up on these resources. Will give you much more clarity than hearing me talk about it in the next 5 minutes. But broadly speaking, so AWD LSTM is a way within So LSTMs are basically long short-term memories, and they're basically a specific form of deep learning neurons architecture which helps you handle sequences. This particular framework helps you tune that, and this is one of the secret sources which is part of ULM Fit. Right? So the big takeaway from here is that this algo helps you train your language model better, faster, so that you actually reach convergence. Okay, so let's talk a little bit about the data, the experiments that we conducted, and some of the results that we obtained. So this is kind of what we used. Right, so we had some Wikipedia data in Indonesian. We crawled that out, we got it. It's a pretty set pattern. It's a pretty ready to use workflow. You can get most of this information. What we did internally is essentially the data scientists within the team went out, spoke to all our business stakeholders and says, give me every single piece of text that we've ever had, right, at Traveloka. It was a hunt, it was a treasure hunt, but it was absolutely something which wasn't really out there. So we had to go out, speak to our PMs, go dig deep into our repositories, of which there are many, go and dig deep into our data buckets, of which there are many, because when you're around for 7 years, you kind of change a few things. So GCS, S3, whole shebang, right? So we ended up with this data set, 6 million sentences, 99 million sort of tokens, words, and no, okay. I need to speak into the mic.
Okay.
Okay. I don't know. Which? Mic is better.
Oh, okay.
This one, right? All right. So okay, I will try and remember this. So what I do want to sort of reflect here is how messy real data is compared to the Wikipedia corpus. So I want you to kind of bring your eyes to this particular number, and this what this f equals greater than 5 means. What this means is, in terms of unique words that were in our corpus, that occurred at least 5 times or more. This number goes up to 1.9 million when we take all of them. So what actually comprises this data set is things like chat logs, reviews, help requests. Right? So people typing an email saying, I need a refund, or hey, I love Traveloka. So they're passionate whenever they're typing some of these pieces of text, which means they misspell stuff. So it's, I guess the message I would say is it's very important to kind of keep handle on how messy real life data can be. I also want to kind of highlight the things in red. I'd love it if somebody could tell me a word that's about 118 characters long. I think I have a pretty decent vocabulary, but I'd love to learn more. Likewise, this guy, I don't know. Oh girl, I don't know. So certainly it's something which you have to spend a lot of time managing around. If I had to quantify the amount of time we spent on doing this work, hands down, most of it was in getting to this part here. Okay? Okay, so then what did we do? We wanted to understand how to use, or how to build a language model which would help us really take our NLP offerings in Bahasa to the next level. To do that, we chose ULM Fit, and the decisions for this are not purely technical. I think they're a bit, the data scientists who are working on this, they love PyTorch, they've been using it. ULM Fit was something they just wanted to try out. We could have gone with Elmo or BERT, which are, again, operating in the similar space. We chose ULM Fit. And we did this. So basically we said, let's have a look and let's make sure that we're trying both things. So let's validate. I think there's certainly a crisis of reproducible research going on in the community. So wherever possible, it's always a good idea to make sure that you're trying to replicate results. Okay. So what we said is let's get a pre-trained word embedding off the shelf and then use that as a starting point. But that's always a good idea, except when it isn't. And then we said, let's try and also train our own embeddings from scratch. I think we've got enough data, why not give it a shot, right? So we did that, and then we said, let's see the impact of accounting for aberrations in our data and not. And we felt the arbitrary, the nice even numbers, it's all about even numbers, but the nice even split, so say frequency of 5 and 10, and say, let's take these corpora, And then we basically split our final validation set into 3. These had all the messy in them, right? So they had no filters, no frequency filters at all. So we ran these experiments. And these are our results. Okay, so this is, we were quite excited when we saw this, because the numbers that you're seeing on the column you need to pay attention to is the perp, which does not stand for perpetrator, but perplexity. And that's basically a measure that we often use to measure the performance of language models. At a very high level, perplexity tries to answer the question, it relates to information entropy, and it says what's the probability that the output of the language model has actually covered some meaningful aspect of your overall linguistic vocabulary, right? So essentially, low numbers are good, high numbers are bad, okay? This is where things get very interesting. So for the keen-eyed among you, okay, so let me briefly describe the structure. So we've got the Traveloka corpus results over there, we've got the Wikipedia Indonesian results over here, and ignore this for now, I'll come to it later. What we did, if you look on the column there, is we also have it categorized by our pre-trained and our own vocabulary, word embedding, and we also have it done by sort of the minimum FF5 or an FF10, as well as on each validation set. Right? So what you see is our lowest perplexity is about 14.01. If you then compare the perplexity of the models in the Wikipedia data set, it's a significant aberration. I can tell you right now, for most of you who are asking, yes, it's probably over 50, right? But here's the weird one, right? The sort of perplexity numbers for state-of-the-art English performance is around 40, last I checked, for Wikipedia Corpora, right? So the fact that we're getting a sort of a 14% number is really, it's intriguing, because you're like, okay, well, if you overfit, at the same time, it's wow, it's a lot higher than what we're expecting, so what can we do with it? So to test that out, we kind of went down this whole character and identity approach, where basically instead of training word embeddings, we train character embeddings. So the biggest difference there to think of it is, if you think of an embedding or a vector embedding in the word space as a word is represented by a number, in the character level space, you're basically taking into account that a vector embedding of a word is comprised of the individual vector representations of the characters. So it's much more robust to spellings or out of vocabulary aberrations, right? So here we did see a bit of a bump. So this is very interesting, because the scientist in us was screaming, overfit, let's not do it. But we said, you know, we have what we have, we'll spend some time on it, let's actually test it out in a real world use case. We did train it on a very interesting email classification task, and we kind of beat some of the top vendors in the space. So our results are heads down, hands down, superior by about 7 to 8% from people who we've engaged professionally to do the exact same task. So I guess that's another challenge. So whenever you're doing production machine learning, try and see if it actually solves your problem before making a final decision. It's often not easy. There are certainly areas where you say, no, this definitely hits all the red flags. And at the same time, there are certainly times where you say, okay, well, I can live with this compromise. So I want to kind of not take too much of your time, because this is actually some of the interesting stuff that I was hoping to get to. So, managing inference latency. Yes?
Can you go back to the last page?
Sure.
So I have two
Sorry, do you mind if we, I will definitely answer. Do you mind if we just finish, just in case? Okay. Okay, so managing inference latency. When it comes to machine learning in production, the biggest sort of jump that a lot of people I find struggle to make is, you've trained a model, you've got your notebook, and it's wonderful, it's beautiful, but now we need to productionize it. So you don't really think about performance when you're doing a lot of the research, but when you type in a search query, there's a lot of research, and it's true that basically the latency at which you can return a result has a direct impact on sort of customer satisfaction with that data product. So to give you an example, for our search platforms, in terms of our intent detection SLAs, we operate on sort of the 100 millisecond threshold, right? So when somebody says, this is a query and I need to understand what this query particularly means or what product it's referring to, we have to give that result back in 100 milliseconds. Now, deep learning is notorious for really taking a lot of resources out there, right? So what we use in PyTorch, so this is something a bit specific to PyTorch, but essentially what we found is trying just-in-time compilation, which came as part of the 1.0 release, has a benefit. So there's certainly an avenue of thought. I mean, you can always, so you've done a lot of benchmarks and you're saying you want to chuck in a 24-core CPU instance, deploy your Kube container over there, and that gives you a certain latency, or you could do it on the GPU, on the cloud, if you're doing it on cloud. But there's certainly a trade-off to be made, right? Because one of them costs a lot more than the other. So if you need to do low latency inference in the deep learning space, it's critical to optimize for. And that's often not something which is widely covered in the literature. So JIT compilation basically takes your Python code and compiles it into C++ as you're sort of serving the model out there at very high level speed. And this is kind of some of the impact, some of the numbers that we got. So on our MacBook, we were seeing a huge difference. So we're seeing a significant gain in terms of the latency for our model serving. And on a GPU server, it's not as profound, but I would say that given that, in any case, most of your GPU interfaces are already pre-compiled in C++, so it's really the final wrapper code which gets compiled. It's not that surprising. The other thing which is pretty new, is highly experimental, but it's something which I think people should start talking about a lot more is the sort of pruning. So pruning, essentially, if you kind of look at most deep learning models, after they've been trained, they're still quite sparse. And what that means is if it's sparse, then the chances are that a particular neuron or a particular layer or a particular section isn't really contributing as much to the decision for your particular case and data set as it could be. In which case, why not drop it? Right, so think of it like sort of compressing your deep learning trained model. There are various approaches to do it. We were using PyTorch, which is why we didn't go with the Google implementation, but Intel and Nirvana have kind of they've developed Distiller, and they had a pretty interesting code base. So that's kind of another thing, right? So when you're doing some of these machine learning in production, you're often constrained by time resources. So you say, well, I don't have 6 months to do this, so I can't really build or write this paper from scratch. Is there a tool out there that I can really grab and work with? So what we did, and the reason, again, I'm putting highly experimental here is because we've tried it out, it's worked for us on a very specific use case, and I just wanted to give people a taste for some of the avenues that we have to chase. Chasing performance. So we managed to get, I think, a 30% for our best trade-off. I think we got a 30% reduction in our model memory size, and that resulted in a sort of 2.3% drop in performance. Inference time was more or less static. Okay, so the other challenge when it comes to productionizing machine learning is you have to think about model staleness. Oftentimes, in fast-moving tech companies, you release products which are quite new, not just to your company, but conceptually, right? So sometimes you don't actually have data on how people are going to use your product. In which case, what becomes really important is your pre-production model performed at a certain metric. You're like, I'm really happy with the precision of it. It's beautiful, it's fantastic. And then you launch it, and people are using it in very different ways. I mean, we've seen people put in math equations in our platform. And you're like, why would you do that? But they do it, and then you're like, okay, well, and the PMs are screaming, customer satisfaction. So anyway, so some things like that happen, and you have to account for it. The message is, figure out a way, once you've deployed a specific product, to be able to loop back and iterate very quickly. What we're trying to do at Traveloka is basically adopt a bit of a reproducible research paradigm, and we think there are 4 things that you need for every machine learning model in order to be able to draw a line back and repeat and iterate. The data, so what's your training data, what's your validation set, either snapshot it, or if you're comfortable, if you think your data stack allows for it to be repeatedly sampled, then store the query, but store it somewhere. The second piece is the model itself. Here, we recommend doing both your source code, naturally, and of course the artifact as well. Because sometimes there's often a discrepancy between, you've got the repo, you've got the data, you trained it, but somehow when you store it in whatever storage of your choice, and then you put it in your Docker container, it got corrupted, and you want to make sure you're isolating issues like that. So store both. The third thing is hyperparameters. So obviously when you're kind of training machine learning models, especially in the deep learning space, they're so sensitive to hyperparameters. In fact, so even things like set seeds have been shown to have a significant impact on your loss and conversions. So store those as well. And finally, you've got, okay, so you've kind of got your data, you've got your model, and you've got your hyperparameters, but do you know what result that actually got you, right? So make sure you're versioning that as well. So these are the paradigms that we're trying to adopt. It's a really tough problem, by the way, so if anyone has any solutions, please come and speak to me. But we're trying to get there, and I think in the interest of time, I will skim through this. This is the other thing. When it comes to training, we got lucky, but it kind of took us sort of 10 days for our Traveloka corpus on a B100 GPU machine, and 6 days for Wikipedia corpus. This could have easily taken a few weeks. In fact, for some of our early iterations, when we were trying things out, it was just constantly training for a week. So then, when you're thinking about how do you get a training pipeline for something which is slow-moving yet needs to be deployed very quickly, or has a sort of it's got a dichotomy there, right? It takes a long time to train, but the data that's powering your algorithm and the conditions under which your algorithm is successful change quite quickly. So it's important to kind of go with a so invest in effort. So don't underestimate the amount of effort and time it will take you to go from a notebook to a full-blown, streamlined feedback, right? Okay, so again, some of the key takeaways. Some of these are not directly. Think about performance and inference. So these are one of the challenges which will hit you whenever you're coming up with an algorithm. Don't optimize prematurely. So hands up, we've done absolutely no hyperparameter tuning for our AWD LSTM work. We've just taken the ones that were on the paper and the repo. We haven't had to so far. If we need to, we'll get there. I just feel that it's something which you should do if you genuinely feel it adds value, or if it's not solving your problem, right? Finally, I think this is an adage which people underestimate. It's also something which actually people take a lot more lightly when it comes to working with image or NLP data. Or somehow, just because you don't have the classic EDA lifecycle in more sort of quantitative or feature specific machine learning life cycles, and think, no, you don't really check your data. Well, yeah, guess what? I mean, it was a learning process, but the first iteration, which took a few months, was because the gentleman who was doing the experiments didn't check for frequency, so to do it, right? So I guess that's really my key takeaway. These are the 3 big key takeaways. I hope you enjoyed the talk. I'd be more than happy to take any questions. I'll go back to that slide.
So please introduce yourself, where you are from, and your question.
Hi everyone, I'm Manu from Gojek. I'm a data scientist at Gojek. So my question is, can you name the pre-trained word embedding which you tried? And the second question is, did you actually try training the pre-trained word embeddings on your corpus? Traveloka?
Yeah, so that's a pretty good question. So essentially what we did is we took we're using Word2Vec as our word embedding space, right? So we literally took the Word2Vec embeddings that were off the shelf for Bahasa from their official repo. And when I say kind of pre-trained versus non-pre-trained, so just to clarify, we took so the biggest difference here in the experiment protocol is we either started with those pre-trained embeddings, or we went completely vanilla and we said, let's start from scratch. Let's rebuild our own Word2Vec on our Wikipedia corpus.
Which one performed better? When you trained on pre-trained?
So here what we're saying is when we didn't use pre-trained, they perform better. So false here means basically so this is basically the fact that we did use the Word2Vec, here we didn't, and this basically, well, when we sanitize it a little bit for frequency of words, this is what performed best for us.
And in case of vector, did you use like CNNs or LSTMs?
No, sorry. So this is character level embedding. So not RNNs or LSTMs.
We will take one more question and we'll leave the rest after Yushen has speak. In the interest of time. So please introduce who you are.
Hi, I'm Raymond. Okay, yeah. So my question is that I don't. Oh, hello. Is that very?
I can hear you.
Yeah. Okay. So my question is that why do you actually need a real-time prediction for? I'm getting that basically this is you're generating a word embedding, right? You can always make inferences for the result and then basically just put it in a calculator because it's just word embeddings, right, at the moment.
Yeah. So not quite. I mean, basically the way we kind of use this infrastructure is we will then plug in a classifier on the end of this entire pipeline. So the word embeddings then go through the language model followed by a final classifier. So that's where the inefficiencies come into play. So for example, maybe perhaps, so we use intent detection and search as a use case, but if you're thinking about natural language generation, right? So here's a query, you understand what it is, but now you want to respond. When it comes to that kind of space, then latency becomes critical. I mean, sure, you can always try and fudge it by trying to simulate, the robot's thinking, and then, but it's better to err on the side of when you really need to respond.
Could I just ask one more performance
Sure,
question?
sure, go for it.
Sorry. Okay, so in that case, because in Indonesia, the GPUs are not generally available for most cloud platforms, and I guess that network latency is one of the major issues. How are you getting around that?
So that's an interesting one, right? Because when it comes to the stack that we've invested in, obviously AWS, GCP, they do operate in Singapore. So when it comes to handling GPU inferences, it's important to make sure that you're, that's how we're getting around it, right? So we don't really have any GPUs in Indonesia or the Indonesian cluster, so we have to work with the limitations we have. So that's why it becomes, so I guess we kind of think of this as the pie that you have to play with from the customer perspective. And then certain components keep taking chunks of it, and then finally in the end, maybe the machine learning team has like, this much to play with. Fight hard for that. But yeah, I guess the answer is there's no easy solutions. We'll try our best.
Hello everybody. So I'll be speaking about making dynamic personalized recommendations, the algorithms and the data that's required to serve these kind of recommendations. Okay, before I start, actually, there's a URL at the top that if you want, you can use to ask your questions there. The audience can also go in and vote for the questions you want to be answered later. Yeah. So I'm Yushen, currently a data scientist at Traveloka. I'm the recommender systems team. Previously, I was actually a data scientist in Lazada. Yeah, and given my experience, I've worked in public service and then e-commerce in in Lazada, and then finally right now in the travel field in Traveloka. I've worked with problems in various domains such as language, recommendations, images, and fraud. And my education background is actually a Bachelor of Science in Statistics from US. And these are the tools that I use. They are familiar with TensorFlow, Spark, Kubernetes, and in Traveloka we use the Google Cloud Platform a lot. This enables us to apply machine learning on a scale of data. So this is the agenda I have for today. First of all, why do we want to do recommendations, product recommendations? And then I'll cover some use cases of what recommendations can do. Next, I'll give a simplified overview of what architecture is required to serve recommendations. And then I will be covering one recommendation algorithm, which is called the Smart Adaptive Recommendations. Inside it actually involves two models, which is the Severity Model as well as the Affinity Model. Then I'll explain how they are put together to derive personalized recommendations. And finally, I will cover some implementation details before I conclude. So why do we want to do recommendations? So the primary reason why we want to do recommendation is that recommendation actually assists in product discovery as well as decision making. In most internet companies, we have observation that looks like this, but we have a lot of products. But then actually the popular products form a very small, take out a small proportion of your product catalog. And there's a very, very long tail of products that are relatively less popular. This is also known as the Pareto principle. So there's a important few followed by a trivial many. So recommendations actually help discovery of these products in the tail end because these products are niche. They probably only fulfill the needs for a selected few customers, and recommendations actually help to display these products into the customer's app or website. So another reason recommendation is useful is that, especially if recommendations are personalized, it promotes customer satisfaction. This is especially so when the products that are recommended are relevant to the product, so the user. And having real-time personalization actually further encourages user interaction because if they can see recommendations reacting to their browsing or their usage of the app, then they are encouraged to use the app more to see what the recommendations can be shown. So use cases of recommendations, there are many use cases. I'll be covering two that the algorithm that I'll be covering actually touches on. So first of all is the item similarity recommendations. These recommendations are usually shown in the product details page of your application. So this is what it looks like in Amazon. So for example, if I'm browsing for a textbook on social network analysis, the recommendation shows me other textbooks that are covering the same topic. So the purpose of this is to show the users that what other alternatives you can consider giving them a look at this particular item. So the next kind of recommendation is personalized recommendations. This is from Netflix. These kind of recommendations usually appear in the homepage or certain landing pages. And recommendations like this are usually based on inference on users' preferences. And it has the purpose of showing users what they may like, even though they may not be looking for it yet. So next, I'll be giving a simple overview of what most recommender systems actually require. So this is a very, very simplified overview. It usually consists of 3 steps to derive. So to get 4 different components. So first of all, we start with the user interactions or the data of the users using our website. From there, we select item candidates to narrow down your catalog. This is important, especially if you have a large catalog of data, of items, and then you come do product scoring for all the items in the specific amount of time. So doing subset of the product catalog is very important in this step. So after we have the item candidates, we will go to the next step, which is doing scoring of the items. Then we derive a ranked list of items. And then from that ranked list, we take the top K and then we display to the user. So on these various steps, there are various models that can be used separately. So for candidate selection, most of it is actually doing some form of user inference, doing segmentation, or inferring users' preferences on maybe their activities, their spending power, their brand preferences, and then from there we can select candidates based on that. And then with scoring items, obvious use case, so obvious model is doing some relevance modeling, prediction, and scoring. So I'll be covering just one algorithm. It's called the Smart Adaptive Recommendations algorithm. Actually, I've been doing this also in Zara, and right now in Traveloka. The concept behind it is quite simple. I didn't actually think there would be a name for it, but I saw this in a Microsoft website. So I don't think they claim to invent it, but they name it, so I'm just going to use this name. So this is the overview of the model architecture. It's very straightforward, very simple. We only start with one data that's required, which is the transaction data. This is actually the user browsing data. Only 4 fields from the user browsing data is required: the user ID, the item ID, the time of the interaction, as well as the event type. So the event type will be something like page views, add to cart, checkout, and then purchase. So from there, we derive 2 separate models. First of all, with the item similarity, building the item similarity matrix, and then after that, also getting the affinity matrix. Then after that, we combine these 2 models together, and then we get a list of scores, and then we take the top K items. So don't worry about the picture. I will be showing this repeatedly in the next few slides. So the characteristic of this model, of this algorithm is that it's actually quite straightforward. It's only based on 2 concepts, item similarity as well as recency to similar items. In terms of the type of recommendation model it is, this is a model that's based on collaborative filtering on implicit feedback. So collaborative filtering means that it's based on users' interaction as opposed to content-based filtering, which is based on the item attributes or the user attributes. And then implicit feedback means that we're not asking users explicitly to grade the items, but rather we are inferring their preferences based on how often they look at certain items. This algorithm is able to serve real-time personalization. I'll show you how it works later. And also the benefit of this algorithm is that it works on new users as long as they have at least one click, one interaction on the website. Unfortunately, this does not work on the cost-up problem for new items. But actually, this is not a major problem because given that personalized recommendations, we have a limited real estate, so we do not have the luxury of providing scores for all the items anyway. So we probably can show up to 10 items, 20 items, and most we will not be able to, we don't have to score all the items. And then finally, this algorithm is able to serve both recommendation use cases I mentioned earlier. So I'll touch on each of the models separately. So starting with the similarity model, which is actually at this part of the model architecture. So how do we get the similarity model? From the transaction data, the first thing we need to do is actually to construct this item co-occurrence matrix. You can also think of this as some form of market basket analysis. We are trying to find for a pair of items, what is the number of times they actually appear together. You can count based on checkout, number of cards that 2 items appear together. Or in my case, I actually count the number of times, number of distinct users that has interacted with both item I and item J within a predefined period, for example, 1 week. So this matrix is actually a square matrix where each dimension corresponds to every item in the catalog. And then the X, the values inside, will be the number of times, number of distinct users that actually interact with the item. So how do we derive the co-occurrence matrix? From the interaction data, we use 3 columns, the user, item, as well as the time. And we do a self-join by the user. So we get duplicated columns for the item and the time. And then if we take the difference between the time, right, we can get the durations between interaction of these 2 items by that user. So we can further down and do some filtering of the interaction based on the duration between the interaction. This is important because if we want to consider, we only want to count interactions that are close together, for example, 1 week instead of counting interactions that are like months apart. So after we do filtering, we group by item I and item J, and then we do count distinct user. Yeah. So one important thing to know is that in order to do this, you need to have a very efficient kind of query engine in order to support the large data. Yeah, so how does this actually correspond to the co-occurrence matrix? Is that actually the item I, you can think of it as corresponding to the row, item J corresponding to the columns, and then the count will be inside the cell, inside the square matrix. So after we get a co-occurrence matrix, the next step is usually doing some form of matrix factorization, as shown here. So an interesting thing to note with regards to matrix factorization, usually we get a latent vector, so latent vectors, there's a compressed form. You can actually imagine the latent factors actually is also deriving a form of embeddings for the item. So for example, if you look at latent factor U in item I is actually represented by an embeddings of 3 dimensions. Similarly for latent factor B, item J is represented by an embedding of 3 dimensions. Then we'll use the embeddings later to calculate the similarity. So in terms of matrix factorization, there are a few obvious algorithms that we can use. Alternating each squares, or we can use stochastic gradient descent if memory is a problem. And finally, we can also use the graph model. Graph model is actually represents global vectors for word embedding based on local context, I think. If you look at the paper, you'll see that it's actually doing a form of matrix factorization based on co-occurrence matrix. So the concept is very similar. We can apply the same optimization algorithm based on the same laws in the graph paper to derive embeddings for the items. So after we get embeddings, to get a similarity matrix, it's very simple. We just do cosine similarity on the embeddings. This is a very common approach to get similarity from embeddings. So the whole assumption of this model with regards to calculating item similarity is that we are assuming that items that are similar will be likely to be interacted close together in time by many users. So this item similarity matrix can be pre-computed in batch on a schedule. And then already with this item similarity matrix, we can use directly to serve similarity model, item similarity recommendations. Given item, we fetch the scores, and then we just sort by descending order. We can show the items in the item similarity use case. So next, the Severity Model is also derived from the same transaction data, and then we use later. How do we do that? this step is relatively more straightforward. It's just a bunch of computation. From the user interaction data, we actually calculate two values, applying time decay based on the time of interaction, and then having separate event weight depending on the type of event. So, of course, we want to weigh like events such as purchases at a higher score than an event such as a view. Given these two columns, then we just multiply them together to get a affinity score. So this actually takes into account the type as well as the recency of the interaction. And you can see the formula here. W represents the weight of the event, and then this exponent here is a time decay with a certain half-life. So big T is a hyperparameter you have to define, predefine. Depends on what you want to use. I think in general, like using 24 hours or 7 days tend to work well. So from this, you will get an item affinity vector that looks like this. And the assumption here is that users have preferences based on the item they recently interacted with. If you think about the item affinity vector, it is almost just a recommend showing the last few items, so it's not very useful by its own. But the item affinity vector will be used later to derive the candidate items that we will show to the user. And what's important here is that in order for personalized recommendation to be able to be done in real time, this item affinity vector has to be computed in real time. So how do we put together the two models to finally get the personalized recommendation score? It's actually very straightforward. It's just a linear algebra. Yeah, so given the affinity vector and the similarity model, you do a dot product, you get a set of relevancy, user item relevancy score. And given this score, you just do a sort in descending order, take the top 10, top 100, then you can make the recommendations to the user. So the concept is such that for each item, right? So user, the item, for each item, it has high scores only if it has very high similarity to many recent items that the user has interacted. How do you get that? Is that given this formula, in order for R to be high, it has to have high similarity with many items, and then these items, ideally, they are also recently interacted. So the affinity score is be high when it's recent. Yeah. And also, it has to be computed in real time, because similarly, item affinity vector is computed in real time. So the matrix multiplication has to be done in real time, and then you get the real-time scores for the relevancy. So I will next cover some implementation challenges as well as possible improvements. So I've been saying the need for the affinity vector to be calculated every time. This poses actually some very important engineering challenge. First of all, we need to have accessible live tracking of the user interaction logs. What do I mean by that? Is that in order for the affinity vector to be computed in real time, first of all, we need to be able to track the user's interaction in real time. That means once the user has clicked on a certain web page, it must be inserted into the database. And not only that, that database must be able to, must be able to retrieve the information in the database in low latency immediately. So this poses actually a very strong engineering challenge. And then next, of course, doing the computation of the linear algebra, we need to have some way to efficiently compute the dot product. But this is not really a problem nowadays with very efficient linear algebra libraries.